Good afternoon. I think I'll start because I have more slides even. And so when we sort of parted in the morning, I was presenting briefly Tarkin's theorem, and the main reason I did this was to raise doubts in you that a state is a very clear concept. I will continue for 2 more slides discussing the notion of states. So what we have seen this morning, that there is something like a balance or equivalence between defining a state intuitively or philosophically as everything that is currently the case. That's reality, a slice through reality. Everything's there. And then we have the Markov idea that the physicists have. Or, in a sense, for information theoretic and modeling reasons, one could just as well identify a state with history information of lower dimension and of observations, which in a sense makes a little bit more sense philosophically, because these observations we really have, whereas the state, the system by itself, das Ding an und für sich, like a good philosopher might say, is something we in a sense don't have. We just assume it's there. So I'm glad no philosopher is here, because it's probably much more complicated than that. So, and there are a number of formalisms that, in a sense, directly build on this idea to define a state by previous information. These are, we mentioned the delay differential equations. In them, it is directly on the surface. Then there are Markov chains called higher order Markov chains, where the future probabilities are defined not only in the terms of the current state, but a few previous states as well. There are things like filters that I will introduce later. And that's one thing that I sort of, with a bleeding heart, do not introduce at all in any detail in this lecture, is the general formalism to write down stochastic processes. These general formalisms also are very non-Markovian and essentially identify a state of a system with the entire previous history. So everything that has been before is sort of collected and condensed into what in that world of modeling is the state. So the idea is what happens next at time n+1 in the general way of writing down distributions for stochastic processes. It depends on everything that has happened before, from starting time 0. So that is one thing that sort of is a take-home message from the previous session and from this slide. One can sometimes, or maybe even always, consider a state also as just a collection of previous information, an encoding of previous observable observation. Okay, so now there's another way of looking at states. Namely, so far we looked into the past to define a state. One can, in a sense, just as well look into the future to define a state. So in this sense, a state is something that encodes what can be seen in the future. Not what has been seen in the past, but what could possibly occur in the future. So there is a new, well, I think there's more on this slide, yeah. So this has actually been done. So there are a number of formalisms available whose state representation are what they call predictive states. So it's called predictive state models or observable operator models, or in theoretical computer science, they are called multiplicity automata. And this has a tradition in signal processing as well, where I don't think it is so prominent, by Lotfi Zadeh. There are so many Zadehs that have had given substantial contributions to all kinds of signal processing, engineering, physics, general computer science. So if you see Zadeh, it's not only one person usually. So this is one of them. And he, in a theoretical paper where he discusses the nature of state concepts, he says, the state of a system at any given time is the information needed to determine the behavior of the system from that time on. So according to this view, and he says that's the hidden view among physicists, everything that really is important about a state is that it defines how the system will continue into the future. And okay, and if we find some way to encode the future at the present time, then we have another state representation. And that is done in these models here. And I have been working myself in these models, so I know them quite well, but I have no time here to go deeper into them. If you want to do some Google search on them, go for predictive state representations or observable operator models, and then you will find the basic mathematical formalism to turn future information into current states. So they are particularly important for machine learning tasks, because if you look at state representations that are future-oriented, then one suddenly has access to a new kind of learning algorithms called spectral learning algorithms that are, in a sense, amazingly efficient sometimes. Okay, so I have to leave this topic. Not only do I confuse you, hopefully, I also frustrate you, because, hopefully I do, because I always sort of say, this is nice, I say it's fundamental, you should know about this, and then I flip to the next slide and you don't learn anything about it. That's how an overview talk works. So, now a new chapter, namely a whole, let's say, the engineering view on modeling temporal change without even introducing a notion of state at all. That's also possible. State-free modeling. And the idea is like this. An engineer, as I mentioned in the first session yesterday, an engineer is basically interested in the input-output behavior of a system. So input to a car would be your steering commands, the output is where it drives. Input to an amplifier is a low amplitude signal, output should be an undistorted high amplitude signal. So input-output transformations are what the system engineers are really after. And they have found a way, the classical 100 years old, not multiple hundreds, only about 100 years old, formalism is what they call system of filter is just a way to directly map input sequences into output sequences. So if you hear the word filter or system said by a signal processing person, not by a physicist, then they just mean a function that they typically call h, which just takes entire trajectories, entire signals, so they call a timeline of a scalar quantity a signal typically, which takes input signals into output signals. So it's just a map from time series to time series. So the state dots that I have shown on all my previous slides are gone in this picture. All you have is a map from time series to time series. What is a time series, mathematically speaking? It's a function from time points to values. So therefore, the mathematical nature of a filter or a system is a map between functions, from functions to functions. Sometimes they are called functionals. And this makes, if everything is done as simply as possible, then everything is linear. Then one lives in a mathematical world of linear functionals, and that is functional analysis. That's the part of linear algebra that deals with this. And that's the background math for this kind of dealing with time. So the filter is just such a, any such mapping is a filter or system according to the, so the words filter and system are basically equivalent for signal processing people. Yeah, okay. So how can you navigate or how can you work with such strange functions or functionals? So, well, one thing first. There is again this distinction between continuous time and discrete time filters or signals. Traditionally, this is at least 100 years old, this kind of thinking. Everything was analog because the digital computer was not invented 100 years ago. Everything was analog, time was continuous. Therefore, classical theory of signal processing and control is from continuous time series to continuous time series. Then with the revolution of digital computing, in fact, all the machines that do signal processing use digital computation where time is hacked into time slices called sampling in time, and values are also discretized, but most importantly, the time is discretized. And so today, a textbook that you buy for basic course in signal processing will be about digital signal processing, not just signal processing, but digital signal processing. And this means time has been discretized. And there are certain let's say mathematical laws that tell you how much information do I lose if I hack a time series into slices, a continuous one, and ignore all the values in between and only are left with the sample point information. And amazingly, under certain conditions, you lose nothing. You can, under certain restrictions, reconstitute the entire continuous signal from the digital one. These are the so-called sampling theorems. So we will not go into this. I will give you a short overview of terminology, of how such systems or filters can be classified. There are very many filters, and one of the most convenient to use ones are the linear filters, where basically it says these functionals, these H maps that take time series into time series are linear maps. That is, if I want to know what is the output signal if I input a linear combination of two signals, then it's just I can factor this out, this one here. I think it's clear what it means to be linear. So the textbooks of signal processing and control, I would say, are concerned 95% with linear theory, and you will see on the next slide why this is so. So this is a very large, elegant, transparent, powerful way of looking at time series, linear signal processing and control, with very beautiful insights, always confined to linear. And why is that so successful? Because for neuroscientists and cognitive scientists, it's clear the world is very nonlinear. The brain is super nonlinear. So why would I be interested in something that immediately, obviously, is inadequate to model what I'm interested in, namely neural processes? Well, the reason is that this is so successful because originally it was used for systems, real-life systems, that in fact are linear to very close approximation. Especially, it was used for signal processing and signal transmission, and these are extremely linear processes, so only at very high energies, signal transmission becomes nonlinear. So that's one reason why this linear worldview had 100 years of time to unfold into a really large body of knowledge, because it was adequate for many, many tasks. So that's one reason. And the other is that when people started to look into nonlinear systems more closely, when I say people, I mean signal processing engineers, they they adopted the linear methods and made them nonlinear by sort of what they sometimes call hybrid systems. They hacked the operating regime of a nonlinear system in small patches and modeled each of them with a linear model and glued them together. So still they could use the linear methods that they were familiar with. They did not want to use neural networks, for instance. What a machine learner would immediately not even think about this, but just write down a neural network and train it with data. Yeah, interesting question. Why do the control engineer and signal processing people not use neural networks? Except that historically they don't know them. Yeah?
Yes, because you cannot access it analytically. So
exactly. It's a cultural thing and a legal thing. So a number of applications of control engineering, the customer wants to have a proof that this robot will not go berserk and just kill everyone in the vicinity, or this rocket will not explode, or this whatever. So you want to have, as a good engineer, something like a safe ground to say, okay, nothing bad will happen. This means you have to prove stability conditions for your systems. And this is just basically impossible for neural networks, but it is very well understood for linear systems. So this is one real factual reason that you accept some loss in modeling accuracy, namely the nonlinear parts somehow you cannot capture. But whatever you have in your system that is linear, if you implement a linear filter, for instance, you can prove it's stable under these and these conditions. So that's one reason. Another reason why signal processing people don't like really thoroughly nonlinear methods is that it's cultural. So they have been. So that's my interpretation. I'm not sure whether this is sociologically true, but they have been trained like this or brainwashed for about, 6 or 7 generations, and this leads to just let's say it solidifies and becomes concrete. It becomes conferences, it becomes tracks, it becomes types of reputation. Everything is linear in this world. And it's very hard to get out of this. It's starting. No, okay, I continue. So linear systems. Then to further terms, time invariant systems. Those are systems where basically it means that as time goes on, the local transformation rules don't change. So if you have an input signal that's transformed to an output signal, and you shift both just by any amount in time to the right or to the left, then you get the same input-output mapping. These systems are called time-invariant systems. And then if you group linear and time-invariant together, you get linear time-invariant LTI systems. So most systems that are investigated in signal processing control are LTI systems, linear and time-invariant. And once you have this, particularly simple and let's say general and elegant tools can be applied. Finally, there's something that you will find probably natural, but I will in a moment tell you that it's not absolutely natural. One often wishes to only consider systems that are called causal. And this basically means that the output at time n is some function of the input at previous time, so only until this time, not into the future. And also the same output of the system itself may go into this equation, but also from previous times. So a system is called causal if what happens now will not depend on the future. So you do not have to know the future in order to know what's happening now. It seems to make sense that real-world systems should be causal and not use future stuff to know what to do now. That seems even contradictory in itself. So, and now I tell you just one little, let's say, thought experiment where non-causal filters are actually used by you in your brain and are used by signal processing people all along. Namely, for instance, in speech recognition. Speech recognition, you could say, a speech recognizer is a filter that gets as input, let's say, a microphone signal. And as output, it should produce, let's say, a letter sequence. So speech to text. So now, both you and these systems would have a little processing delay in producing the output letter sequence from the input vocal sequence. And this is not only this delay because your brain is slow or these algorithms take too long. It is also because this is a non-causal task. In order to really know what letter has been uttered, it is very good to know how the signal continued. So you only interpret the text behind what I'm saying after having a little delay when I already have continued speaking, and in the context of what I have said after, your brain knows how to best interpret what actually was there before. So in this delay it means that you get a better filter, a better understanding of my vocal utterings to your internal representation of what I'm saying, if you just wait a little bit. And that means you break causality. You interpret what's happening at a certain point in the context of what you know will happen in the future. In order to do this in a world where you can't really access the future, it means you have delays. And so non-causal filters are powerful and necessary if you accept delays in processing. But delays, well, why not? Why not have them? Okay. So and then there is one thing, one of many stability conditions. It's not so clear to define exactly when is a system or a filter stable. But one very commonly used criterion for stability is Bibo stability. That is, if you give input signals into the system where you know the amplitude is bounded, so it doesn't exceed certain threshold values. If then you know also that the output signal will be bounded, then it's bounded input, bounded output, stable. And such stability criteria are important for practical use of let's say, in digital signal processing, in all the amplifiers and processing, denoising systems. Whatever you have on your computer and in your cell phones, all the systems should have this stability property. So one slide I devoted to a slightly more detailed account of how these signal processing people set up their maths, so to speak. So, and now I'm talking only about LTI systems, linear time invariant. There's one particular signal called the unit impulse, which is basically 0 all the time except at time 0 where it's 1. So that's a perfect signal. And this signal has a big role in linear signal processing, because if one has an LTI system, one can express the behavior of any LTI filter or any LTI system by a particular little time series called the impulse response of this filter. So if we have some filter which is LTI, and we look at the input-output behavior when the input is the unit impulse, so these reddish dots, and then if it's a causal filter, we will not see any reaction before that time. That now comes such an energy input into the system. And the system will then do something. So these crosses show the system output after this impulse. And this curve or this sequence of numbers is called the impulse response of the filter. And if the filter is linear, then knowing this impulse response, you know everything about the filter. So all further properties are contained in this information. And there are two types of such linear LTI filters. The ones where this response dies out, so you excite the system with a little pulse, it does something, and after a while it's exactly zero again. These are called finite impulse response filters, or FIR filters. And the others are when this excitation continues forever. It will die out in amplitude, but mathematically speaking, it will always be there. Those are IIR filters, or infinite impulse response filters. And mathematically, there's an interesting reason why you either have a FIR or an infinite IIR filter. Namely, let me just check whether it's on the next slide. Yeah, first of all, FIR filters. You get finite impulse response filters if you can represent the impulse response, or just the output function as, so if you want to know what at time zero is the output in an FIR filter, you simply consider previous inputs, these are the red dots, and you take a fixed linear combination of them. So and then this gives you the current output. So the current output is just a fixed linear combination of previous inputs, finite number. And these are exactly the filters that give you a finite impulse response. And it's clear that they are particularly convenient on a computer. So you just, in a sense, have to install such a vector of weights, and then you get a finite impulse response filter. These filters, again, this is deceptive what you see here. My graphs have 3 dots or 5 dots or something. If you switch on your cell phone, there you will have such an FIR filter very close to the antenna. So at the high frequency end of your cell phone. What does it do? It does a thing called, not denoising, sort of undoing the signal traveling echoes, channel equalization. It does an equalization task. That is, you have an FIR filter close to your antenna that operates at the gigahertz high frequency rate of the high frequency signal, and combines, so the input is an antenna signal, so a high frequency signal. You know maybe that, no, I'm sure you know. So one problem for doing radio transmission and receiving is that there are many travel paths of the electromagnetic waves from the transmitter to your receiver. So if you hold up a receiving antenna, it receives sometimes, if you're lucky, the direct line of sight signal, but it will also receive lots of echoes that have different travel paths. And if the wavelength is short enough, these travel paths will be just very different. So those will be delayed signals. They have each travel path has its own delay. So what you actually get at the antenna, what you pick up from the air, is a mixture of the direct signal, which you may not even get, plus a superposition of many delayed versions of it. And if you want to receive information, you have to undo this mixing of delayed versions. It's called equalization. If you don't do it, you will not be able to get information out of the signal. And these equalizers are FIR filters, and they easily have tens of thousands or hundreds of thousands of these weights. So you have a very long filter. And what makes things even more interesting, so I want to impress you with what your cell phone can do. They have to be updated very often because it's a mobile phone that you carry. So you walk with it, and if you really want to test it, you run with it, or you sit in a car or in a train and move fast with it, which means that the echo paths of the incoming waves will change their mixture very, very often and at a very high rate. So you have to recompute these filters every few milliseconds. That's what your cell phone does. So I just want to, if you switch it on next time, just do so in utter amazement of what you have in your hands. So, but these are just technically FIR filters that that you're using or having, as opposed to the IIR filters. If you also admit that the current output is a linear combination of some previous inputs, but also of itself, of its own output. So if you have output feedback, it's sometimes called autoregressive filters, AR, then you get infinite impulse responses, because if it starts to being excited, this excitation will be dampened, but it will never die out completely. Then you get IIR filters, and they have much more nasty properties than the FIR filters. FIR filters are inherently stable. These can be unstable and go to infinity if the feedback constants are too big. Then you get too much self-excitation. So this was just a brief excursion into linear signal processing. Why I'm telling you this, maybe it's on the next slide. Yeah, I will be very fast here. I told you that the linear signal processing people have invented in 100 years of work a large understanding and toolbox for processing linear signals. And they have found one thing in particular that is a key to why linear signal processing is so powerful. They found that if one takes the original time series, so this S of t is some signal, and computes what is known as a transform into frequency domain, known as, there are several versions, Fourier transforms or Laplace transforms in the continuous time, and well, there are a number of names. Then you get another representation of the signal, basically which you can understand as a mixture of frequencies that go into the original signal. If you have this, then there's one key to efficiency in manipulation these signals and systems, namely that the system transfer function, this h, that takes a time series and returns a time series, this can be mathematically, it's not so, you're dealing with functionals. If you want to apply, for instance, an FIR filter or so an autoregressive filter on a time series, then you have to do what is known as a convolution operation in the time if you do it. So I'm just throwing words at you. If you transform everything into the frequency domain, then this application of a filter on a signal to get an output filter becomes multiplication of two signals, of two frequency domain representations. So in a sense, what a system does, or if you have two systems and you combine their effects, just becomes multiplication in a suitable space. And if you want to undo it, it becomes division. So to do the inverse transformation becomes division. So you can use just normal arithmetics, in a sense, to analyze very complicated transforms between time series. And this is why the linear system people use by reflex these frequency domain transforms instead of what you think is probably more natural to look at the signal, namely as just a signal, because then they can use basically algebra to understand what is happening in the system. And I just mentioned this. And for non-engineers, non-signal processing people, most of you will not probably be signal processing people, but you will be, the neuroscientists among you, you will be handling signals at some point. If you're empirical, who is doing empirical research with signal recording devices? Are not so many. But, well, the pre-processing stages in your signal processing interfaces to your computer, they use such methods, I'm pretty sure. And also, in theoretical neuroscience, there is a tradition to apply these tools to understanding what happens in brain signals. It's not the only tradition that went into neuroscience, but it is one of them. So it's good to know this stuff for neuroscientists. For social scientists, I think it's irrelevant. I wouldn't know theories in this. Let's do a sample. Who of you is a social scientist in the wider sense, including psychology, and has used or seen use of such tools in sociology or wider social sciences? Did you see something like that?
Maybe some kind of picture perception stuff.
Yeah, so perceptive modeling, yes, in psychology. But I would say modeling social systems or economical systems, it's not done, not used. So we had this. Yeah, jump to a new topic. Which later we will combine with what we have seen. So I'm still talking about state-free descriptions of time series. So how can we understand, analyze, or describe temporal processes without using the notion of state? And here's another formalism and a way of thinking, namely through what the computer scientists call grammars, and the linguists also call grammars. So what is a grammar in this mathematical sense? A grammar contains variables, again, finite set, call it V. Here in this example we have two variables, S and A. It contains also what they call terminals, that is another set of a finite set of symbols. Here, because it's one of the simplest non-trivial sets, is just two symbols, opening and closing bracket. And then a number of what is known as production rules, that is, how can rules of the type, if I have a variable, let's say A, I can replace it by a string made of a mixture of terminals and variables. So I will give you an example of how such a grammar can produce a long string of terminal symbols. We always start with S, write it down at the top of a tree. This thing is called a derivation tree or path tree. It is a start symbol. Yeah, this is always part of a definition of a grammar. One of the symbols must be declared a start symbol. S, we write it down. And then I check out, okay, what rules do I have that start with S? And there's only one here. S can be replaced by A. So S can be replaced by A. I replace the string S by the string just A. Then what rules are there where I have A going to something? Okay, here is one. A can be replaced by opening bracket, another copy of A, closing bracket. So I do this here. This A is replaced by opening bracket, A, closing bracket. Okay, so now I have this A to process. And you see how it goes. So this whole tree is always sort of iterated and further expanded by whenever there's a variable, check whether there's a rule. It's non-deterministic, there may be several rules, but whenever there's a rule that can be applied, well, you are allowed to apply it, and then you get branching in this tree and so forth until there are no variables left. So at some point, possibly, it's not necessarily to happen, but sometimes it so happens that you have such a tree where all leaves suddenly are terminals. And then one says, this sequence of terminals has been derived in this grammar. Now, why is that of interest for analyzing temporal developments. First of all, it's not a coincidence that these things are called grammars, because they have been first introduced in this mathematical formal sense by Noam Chomsky in order to describe human language, the structure of human language. So the idea is that such a grammar and such a derivation give you the grammatical structure of human phrases. So for a well-formed, correctly formed English sentence, even if it's very long, Noam Chomsky would know how to set up a grammar of English such that you can parse this long sentence that I'm still continuing to produce, comma, and then in the end, even if I make errors and apparently don't stop in my sentence, a good grammar could be found by Noam Chomsky that would still be able to give a parse tree for the sentence that I'm at this moment still continuing to say, including strange noises that I might make. And in the end, you get a structural description of what human brains can produce, period. So that would be the last closing bracket around this. So this is something that Chomsky did in a number of different formalisms. And that's why these things are called grammars, and they later were found to be extremely useful for theoretical computer science, and they were also found useful by physicists to describe temporal processes in nature. Actually, you can do with grammars that you can't do with any other formalism, and this is something I want to show on the next slides. But first of all, there is some connection with time, namely, if I say something, if I produce a sentence, I do it in time. So speaking is a temporal process. So I speak, I have a sentence, give it to Noam Chomsky, he uses a grammar to analyze the structure of the sentence. So grammars are good for finding or determining structure in time, in temporal sequences. And the wonderful thing about this is that grammars are very good at finding what is known as multi-scale structure. So they can find very local structure. Like these two brackets are close together. So they're close, and but because their parent A is just above them. Whereas this opening bracket and this closing bracket, in a sense, are far apart from each other because their parent A is far above them in the tree. So you can define, at least after you have parsed such a sentence, you can define distances and sort of long-range interactions. This opening bracket must close at some point if you want to have a perfectly well-formed sentence here. So this is something that grammars can do, in a sense by design and easily, to give you a very transparent account, which is just given by these rules, of how you have multi-timescale structure in signals. So I will expand on this because it's a very interesting and important fundamental topic in analyzing data. I will skip this. So I will return to grammars in two more slides. So I will first introduce a little bit of more terminology to appreciate the power of grammars. So if one does signal processing, looking at signals with the tools that the linear people have found, then one quantity or one characteristic of a signal that is, in a sense, computed by reflex by these linear people is known as the autocorrelation or autocovariance of a signal. That is, one looks at a signal, a time series, and checks if I have a certain delay, I pass this moving window with this delay over my time series, so I get a number of pairs of points. How are these pairs of points correlated statistically? Do they have a high correlation or covariance or low one? And then you can plot this correlation against the length of the delay. So here, this blue line is a hypothetical autocorrelation function. At 0, this means 0 delay. That's the correlation of a signal with itself, and that is basically the variance of the signal. So that should be actually the maximum value here. That's wrong to plot it not as maximum. And then it also is highly correlated with its closest neighbor in time, which basically means the time series is slowly changing. And then it has 0 correlation with its own partners on the same time series after this delay, and so forth. So, and what typically is observed in many natural time series is that if you plot such an autocorrelation function and try to fit an envelope around it, a sort of a nice looking envelope, that you can do this with an exponential decaying function. Yeah?
Is this due to that there's less data left in the time window when you approach the end of the time series? Yeah.
There is no end of a time series. So this goes to infinity. So we can have, in this world of modeling, time series are infinitely long. And so you can, at least mathematically, define what is the autocorrelation of a signal with itself after very, very long delays. Yeah, so there's no stopping of that. So, and one finds typically this exponential decay of autocorrelation, which intuitively can be explained that many natural systems, when they are driven by external input, in a sense leak something. So that the new input that comes in replaces, on average, a certain part of the signal energy that's already circulating inside the network. So if one has this, in a sense, replenishing of internal signal or system signal energy by input signal energy, you automatically get exponentially decaying time series. Also, if you just write down any typical recurrent equation for iterated functions, and you would drive those signals with those systems with some external input, and you are lucky and the whole thing is not unstable, then you will also get this. So it's a very generic scenario. It's hard to not have something like this in input-driven systems that are stable. Okay, so, but now, I promised I would return to grammars. There is also sometimes another thing that is observed, or another phenomenon that is observed, namely that you cannot fit the autocorrelation signal with an envelope that's exponential, but only with an envelope that is polynomial. So where you have this r of d, let's say this, or this d to the minus a, is just a constant to, sorry, d is the delay, it's not a constant. The a is a constant. So it's basically a polynomial, well, not a classical polynomial, it's 1 over something. And then the rate, it also will converge to 0 in the long run. This function goes to 0, but in an interesting way slower than an exponential function. So if you see this, then first of all, people give it a name. They call it power law systems or long-range interaction, fat tail 1 over f law. It has been rediscovered and redescribed in many contexts. It's rare to occur, and now comes the explanation for this. You get this kind of power law or 1 over f behavior in time series signals if there is multi-scale memory in the system. That is, you only get this if the system is able to preserve previous information. Previous information preserving means having long-range temporal interactions, have memory on all time scales. So these systems have a hierarchical memory where they can, in a sense, for sometimes preserve some information, which later is needed to determine how the system will react. That is something that, for instance, you do in your brain when you hear speech. So speech recognition is a multi-scale process. you can, when you try to understand what I'm saying, hello, are we still trying to understand what I'm saying? Yes. So then there are very short-term mechanisms in your brain. Just if I start a word, then just by the nature of English, the next few milliseconds, if I start the word, let's say, telephone. So if I say telephone, then your brain will immediately expect there will be an N. That's a very short-range mechanism. A regularity that statistically is short-term. And there are many intermediate scales of regularities in language signals, speech signals, that your brain exploits, and for which it needs a number of differently timed memory mechanisms. For instance, if I start a long sentence and say many things in between. So now, let's say, the sun is not shining today. So, but you have not forgotten that I started a sentence and you want me to finish it. Period. So you are able also in your brain, and you do it routinely, to have memory spans of a few words. But you have also memory spans far beyond that. So hopefully, the ones of you who were there yesterday morning or this morning, you remember some things I said there, and you use that information to understand what I'm saying now, and so forth. So you really you integrate information from many time scales into coping with everyday life all the time. And this would mean that your processes, your filters, your signals that you process are multi-scale. So your reasoning signals, your language signals, basically the human existence, also motion sequences, moving is also multi-scale, are all multi-scale, meaning that you need this kind of maths to describe them. And now come back to grammar. Grammars are, let's say, the best and classical formalism to identify, quantify, characterize, and play with multi-scale phenomena in temporal data. Unfortunately, it is not clear how such nested time scales that you can identify and observe in time series, if you use grammar formalisms, how they actually are generated. So if I speak, I do not create such trees, because that would put me outside time. I really proceed from left to right, somehow, and not first create a plan of what I'm going to say, and then say it. And especially this is true for longer term things. So it might be the case that I plan one short sentence and then say it, but I'm certainly not planning multiple sentences. It just goes on and on and on. But it will later have this structure. So that's something that is very mysterious, and as far as I can see, mathematicians have not found yet, actually I know, because I'm a supervised thesis in this area, it's unclear what may happen inside a system that it produces such fat tail or 1 over f behavior, multi-scale, that you can nicely describe with grammars, but how is it done? How does the network do this? It needs some kind of memory mechanisms, and from what we have seen about the notion of state, so states we saw may also be defined not only as cross-sections but also as memory buffers, so to speak, of things that have happened. If you want to have time series that produce multi-scale characteristics, you would need a hierarchically organized stack, so to speak, for memory items in order to characterize the states of these systems. And as far as I can see, this is open ground for mathematicians to further develop. I can't offer you a nice formalism that you could use for this. So, how much more time? Yeah, wonderful. 35 minutes. A new part. Are there any questions that can be answered in 5 minutes. Yeah?
So I just read in the previous slide that you wrote there close to chaos, like in between brackets, chaotic dynamics.
Where?
No, just in the other one. Yeah, there.
Where's
one of the points there down.
close to? Ah, yeah.
Close to chaotic dynamics. So where is it close and where not?
I think this is motivated by a trend in machine learning neural networks, where there is a mythological thing called edge of chaos computation, close to. So the idea is that if one drives a neural network, a recurrent neural network that produces time series, if one drives it by the correct parameter settings close to chaos, but not quite, then you can get close to these long fat tail dynamics. And it is then claimed that these networks can do particularly intelligent signal processing. So forget it. I can give you pointers to this. I'm a great critic of this line of reasoning. I don't believe it. But you find literature on this. Okay, so now comes the part that is, I think, the most popular and also the part that produces the nicest pictures. So attractors, bifurcations, chaos. So that's what I think students usually expect when they come to a course on dynamical systems. And of course, I must also say some words on this. Yeah, so maybe the important thing is the terminological footprint. So you may have heard about nonlinear dynamics, dynamical system theory, self-organization, pattern formation, emergent behavior, cybernetics, synergetics, and other jetics. So that is a very, let's say, romantic, colorful, powerful, elegant, insightful field that has made it into the public press in many ways. You have seen fractals, you have seen chaos, you have heard the butterfly effect of the weather predictions and things like this. All of this belongs to this field. But as I think I now could demonstrate, this is only a part of the wider areas of describing time. Okay, so and I will now give you a short, concise introduction into basic mechanisms in such systems. So, and I will just do this with one example that just gives a very nice graphics. So I will consider a two-dimensional system, continuous time. So most of this is done in continuous time. The classical results are in continuous time, and systems are described by ordinary differential equations. So this is an ordinary differential equation in two variables, r and theta. Theta, yes. And this is in polar coordinates. So in polar coordinates, you don't have x, y. You have a radius, r, and an angle, theta, in order to determine a point. And we will see that this is particularly nice for discussing effects here. So, and that's the system equation. So the radius changes by this. We don't have to understand it at this point. You will understand it in 15 minutes. You will really understand this equation. And theta dot equals 1 means we are basically looking at a system that is always, where points are always rotating around the origin with an angular velocity of 1. So it takes 2 pi time steps for a full rotation of the system. So, yeah, describes the motion of a point in R2 in polar coordinates. And the one thing that we will investigate in much detail is the role of this A. That's a constant. It's a parameter that you write down into your system equation, and things are what you will observe will depend in an amazing way on the value of this A. It's called a control parameter. Okay, so first I want you to get more familiar with this equation. How does that look like? So a bit more in detail, same equation. And this A I now set to 1. So it's minus R3 plus R simply, because the A is now 1. Theta equals 1. So one way to describe what's happening in such systems is by way of what is known as a vector field or as a phase portrait. So you simply plot what is known as trajectories of the signal that follow the guidelines of a vector field. So if you transform this back into the Cartesian coordinates in x and y, you get also a vector field in x and y, so the temporal change in x and the temporal change in y. So I didn't do this here, this transformation, but that's just an ordinary transformation of coordinates. And each of these vectors plotted here shows, basically it's a velocity field, shows a local velocity of a point. So you could imagine this as a driving field, which whenever you put a ball into it, the ball would be sort of guided and led forward by these little arrows. It's hard to see that these are arrows here in this resolution. And they would always locally follow these arrows on a trajectory. So that's the way how ordinary differential equations can be visualized. And I can't explain this now in much detail. I hope that you have seen similar things before. Yeah, this is a close-up look, which I will not go into because of time reasons. Okay, so now I want to discuss what is actually happening in this system in a global view. So if we have this vector field, this force field you could say, and we start a system evolution by just starting at time 0 at this location where we have this starting point, then these vectors will guide the evolution or the motion of this point always in parallel to the local vectors, and you will find that it winds up into such a cycle. Just if you always locally follow these arrows, that's how you will end up. These arrows are, let's say, visual noise. It's nicer even to plot these things without the arrows. And then one comes up with a graphical format that is called phase portrait. So you simply draw a few sort of instructive examples of these trajectories, which just gives you a visual impression of what happens in this system. So what happens in this system? Whenever you start outside this circle, which happens to be the unit circle, your system will move towards the circle and start spiraling up on it. If you start inside the circle, the same thing will happen, only that your evolution will sort of approach the circle from the inside. Okay, so that's instructive. This is something we can understand by visual inspection. Now, what happens is that this cycle for this equation is what is known as stable. It's an attractor. And now I will use 1 or 2 slides to explain what this means. And also the maths why we have this attractor. So the fact that our angular velocity is 1 just means that all of these evolutions, if you just would look at them with a radar, where do they move, how? They would always be rotating around the origin with this fixed angular velocity. So this is in a sense a boring component of the dynamics. It's very simple. It just means the whole thing is always rotating with a constant speed. What is really interesting about this dynamics is what happens in the radial direction. So the distance to the origin, which is this r, how is that changing? And it's changing by an equation that depends only on the radius itself, so not on the angle. So I will now look at the dynamics in the distance to the origin. So we see here the distance to the origin is fast decreasing, but once you come closer to the unit distance, you get slower and slower. And if at the unit distance, once you are on this circle, you remain on the unit distance. So why is that so? That's quite easy, and that's on the next slide. So I will now only look at this single equation here. R dot is, so forget the angular rotation. Just look at this here. And I now plot here this equation, R minus R3 plus R. So that's this blue plot. It's just this equation here. So it's a cubic. Minus means it goes down in the long run. And plus R means it doesn't go down immediately. It first rises up a little bit and then goes down. If you think about where does it cross the 0, well, you find at 1. If R is 1, then this whole thing is 0. Also, if R is 0, the whole thing is 0. So you get the two zeros at the radius of 0 and the radius of 1. So what does it mean to be 0? It means that the radial velocity is 0. So meaning if this blue curve has a value of 0, then the distance of this rotating point to the origin will not change, because the rate of change is 0. So which means that at a distance of 1 and at a distance of 0, that is directly in the origin or on the unit circle, once the evolution is there, it will remain there, because the distance will not change anymore, because the temporal derivative is 0. If you are starting inside the unit circle, that is at a distance less than 1, this derivative is positive, it's bigger than 0, mean you get a growing value, meaning you approach the unit circle from the inside. The distance grows until close to the unit circle, you slow down and it gets 0. Same, or let's say the inverse phenomenon, if you start from the outside, this branch is negative. That is, the rate of change for distance is negative. Distance gets less. You grow towards the origin, but only until you hit the limit cycle, this unit cycle. So I think this is understandable. If here we have a equals 1, so it's not shown, this parameter, because it's 1, then we get a curve for minus R3 plus AR that looks like this, and we get this phase portrait, which has a so-called attractor at a circular attractor at the unit distance from the origin. Yeah, a bit of terminology. We have two very specific places in this phase portrait. One is actually the origin itself. If you start your trajectory exactly at the origin, then what happens? It remains there, because the radial motion is 0, as we have seen, so it doesn't go away from the origin. And in a sense, rotation it can't do. If you are in the origin, you can't rotate anymore, so you just stay there. It's what is known as a fixed point. It's also an unstable fixed point, because if you would just give it the slightest kick away from the origin, this positive branch of this cubic would start pulling it towards the unit cycle. The unit circle. The unit circle is known as a cyclic attractor or periodic attractor, because once you are on it, you remain there. And if you are slightly pushed away from it by some perturbation, you will be attracted, pulled back to it. It's a stable system behavior. Okay, we will see many more crazy things in the next slides. So, now I do something to the system equation. Instead of the simple one that we had before, I do something to it. Actually, what I did here, I added a perturbation. So the vector field was the original one plus a slight other vector field. And then I get a phase portrait that looks like this. It's now wobbling. It's a weird thing. I'm not going to explain it in any detail. But what you see is that it still looks somehow similar to the previous one. So this clean circular limit cycle has been replaced by one that has this wobbling in it. It's not circular anymore, but there's an unstable fixed point in the middle. If you leave it, you are attracted towards this attractor, and if you're outside, you're also attracted towards this attractor. Although I did something crazy to the system equation. So I somehow messed up the equation, but what I get is not looking messed up, it just looks a bit distorted. Okay, so why is that? Because, no, I'm not explaining why is that, comes on the next slide. If you see this behavior, then one speaks of a phenomenon called structural stability. Structural stability means exactly this, that you have a system equation, that was the original one, the simple one, which has the property that if you add something to it, if you change the vector field that belongs to it by adding a slight other vector field, then of course you get a new system dynamics, a new differential equation. But if this new differential equation gives you a new system dynamics that looks similar to the original one, up to what sometimes called rubber sheet transformations. So you could map this one-to-one on this by, in a sense, printing this on rubber and then pulling and tearing on this rubber sheet until it looks exactly like this. So you have a continuous transformation from here to here. If that is possible, if you have such a rubber sheet transformation, then one says it has the same structure as this, the same topological behavior. And if a system has the property, like this one, that whenever you change the system equation by a small enough but arbitrary change, you get another system behavior that is structurally similar. So you don't destroy the structure of the system, you only destroy a little bit or change the metrics a little bit. Then this equation is called structurally stable. And the system equation that we had before was structurally stable. So I could add some fancy looking sine stuff to it and still you get this here. So it was structurally stable. There's also structural instability. So here, if I take r dot equals 0, theta dot is 1, then what is the phase portrait? I just get, well, circles. Because this means I never change the distance to the origin, and I move in a constant speed in angle. So it's a very boring equation, and the phase portrait would look like this. So these are just a few trajectories. I start somewhere, I just rotate, rotate, rotate. So now this is structurally unstable, because the slightest addition to this system equation would lead to the following observation. If you start here, let's say, you turn around, turn around, turn around, turn around, and if there's a slightest change to the system equation, you will not hit exactly the same point as you were before. And if that happens, you get spiral patterns instead of the circular patterns. So the slightest perturbation to this system equation will actually lead you to spiraling behavior. And there is no way to do a rubber sheet transformation from just closed circles to one spiral. There's no way. So these are not structurally similar. And you are kicked out of this pattern into something that's dissimilar in a fundamental way by the slightest change to these system equations. So here I just added just a tiny little thing here. Okay, so now putting this together, a question. So a question about nature and a question about yourselves. Also a question about hydrogen atoms and maybe the universe. So it's a big question. If you write down a system equation, an ODE, and you really are non-mathematician, you just write down fancy looking symbols. You don't understand a bit of what you're writing down. but it's an ODE, and it defines a system, a nonlinear system if you wrote down very crazy stuff. Will this system be structurally stable or not? That is, will the system equation, if you perturb it a little bit by adding further stuff, will it lead to a phase portrait that's the same or not? This question has an answer. And the answer is, so it's just like the Oscar thing, the answer is, well, yes, it will be structurally stable. So I can say most system equations, in a sense, in a mathematical sense, all system equations, except for ones that have probability 0, are structurally stable. So let's think about this a little bit. If this were not the case, we would not exist. So the fact that you sit here and listen to me means that nature basically is stable. Because according to physicists, you are physical systems. Physical systems are best described by differential equations, ordinary ones or partial differential equations, leading to phase portraits. So look into the mirror tomorrow morning and see a phase portrait. These phase portraits should be structurally stable because you are bombarded all the time by perturbations, by noise, thermal noise, cosmic rays, I don't know what. All of these are slight perturbations. If you would be structurally unstable, then the slightest perturbation would drastically change you. Yeah?
But I mean the unstable systems, as they are unstable, it's hard to observe them, but they might still be there. So.
One has to be careful about unstable systems and structural instability or stability. So a system is called unstable if a normal ODE that describes the temporal dynamics is called unstable if slight changes in the initial conditions will magnify. This has nothing to do with this, because here structural stability or instability means that if you change, so even, how should I say, even a system that's unstable in this sense of magnifying slight initial conditions, or a chaotic system where this is very strong, this effect, it's still structurally stable, because if you change the system equation a little bit, you still have the same instability.
Okay, makes sense.
So the word stability is the same, but it means two different things here. Okay, so in nature and mathematics have the wonderful property that it's normal to be structurally stable. If you write down a random equation, it will be structurally stable. And that's very lucky, because that means that if you write down an equation for you, or your real system equation, you will basically look the same if there's slight change in environmental conditions. If there's a little bit of cosmic rays or whatever, you will perform the same. So for the ones who are German speaking, I know it's not all of you, but I can't resist the temptation to show you a quote from a world where there is no structural stability. So this is from Grimmelshausen, a classical German author, very classical, who he wrote about not the Third World War, hopefully not, the 30s year 30-jähriger Krieg, so 30s-year war from 1618 to 1648. It was a very bad time for Europe, and he survived. He wrote a book, which is a classic in the German literature, and among others, he has a part in his book where he describes a person has the name of the bald anders. Bald anders means soon different, or next moment different. And this bald anders is here described in a very drastic language, or the interaction of the author or the hero of this tale with this Bald Anders. This Bald Anders is an agent or a thing or whatever that just changes its nature and shape from second to second. Not only from one type of person to another type of person, but between animals or between parts. So it's or a flower or a twig. So it always is different from one moment to the next. It's a very strange episode in this book. And in the end, after a short discussion, they actually carry out a little philosophical discussion. And after that, this Bald Anders just flies away. It turns into a bird and flies away. So, and if we all would be Bald Anders, so every time different, first of all, that is not compatible with mathematics. And second, we would have a hard time being. So it's good that we have these laws of maths that tell us that systems usually are structurally stable. Okay, parameter magic. I will now explore a little bit the role of this A. So if A is -1, we have this system equation. R dot is minus R3 minus R. And if I plot this cubic here, it just goes like this. Meaning that wherever I start, the radial component is negative, meaning pulls me towards the origin. Plus I have this rotational component, so what I will see is spirals that home in on the origin in the phase portrait. I think that's obvious. So now if I still use a negative value here, but a smaller one, not -1, but -0.2, then this branch of the cubic still looks basically the same, but it is a bit more upwards, meaning that if you come closer to 0, the minus component is not as strong, so the attraction towards the origin is slower, meaning you have more time to spiral. So this looks more spirally here. Now, if A is exactly 0, then this branch of the cubic has a slope of 0 here, so it's fully horizontal at here, and then goes down. So still you will be, whenever you start outside 0, you will be pulled towards 0, but the spiraling looks crazy. And there is one thing that distinguishes this from that in a dramatic way, namely, if you would try to measure the length of such a spiral arm, in this case it would be infinite. You do not reach the origin after finite travel distance. Whereas if you would measure the length of such a spiral arm, it would be finite. So that makes this phase portrait structurally dissimilar to this one. There's no rubber sheet transformation by which you can unwind infinite long trajectories to have finite length ones. So these are different. They look still similar, but the winding property is dramatically stronger, so to speak. That's due to the fact that here you have 0 slope at this point. Okay, so now let's increase this a little bit, make it bigger. And now this branch again looks basically like before, but if the plotting resolution would be better, you would be seeing it goes above 0 a little bit here until it hits 0 again somewhere here, and then it's negative. So that means outside this green circle, you are pulled towards it. Inside, you are slowly, because you're only very slightly above 0, your radius grows until you hit this 0 point. So you get a phase portrait like this. And finally, that's the one that we already saw. So now I put this all into one sequence. So A goes from -1, -0.2, 0, 0.101. We get on the left 2 pictures that are structurally similar. So you could do a rubber sheet transformation that brings you from here to here. Same here. These 2 are also structurally similar. You could do a rubber sheet transformation that turns this into this. this here is a behavior that you get exactly and only if A is 0. Exactly 0. Then you have spiraling, but with infinite length spiral arms. Here they are finite, and here there are no spiral arms. Here they go away from the origin instead of towards it. So this is structurally unstable. So the slightest deviation to the system equation where A would be 0 would either give you something like this or something like this. Which of the two is hard to predict, but you would get one of the two. So this is now, and this is known, such phenomena are known as bifurcations. So that you look at a system equation that has some parameter that you can change as a mathematician and consider what's happening. This is called a control parameter in this context. And if you pass this control parameters through a certain range, here from -1 to +1, and you observe the following, that for some parameter range, here for all negative parameters, you always get phase portraits that are similar up to rubber sheeting. So then you have a range of parameters where you are in a structurally stable regime. You have another such regime here, but with a different phase portrait that cannot be transformed into this. And then there's one thin line in between where you have, first of all, a switch from this to switch if you go from minus to positive. And directly here you have instability, structural instability. So here you get a phase portrait that's structurally unstable. But you only get this if the control parameter has exactly this real number value. In this case it's 0, but it could be, depending on the system equation, any real number. This is also the reason why the world is so kind to us to be mostly structurally stable. You get these unstable conditions for a system behavior only for exact tunings of control parameters where the real number is exactly hit perfectly. And any change of this control parameter to the left or to the right will give you behavior that is structurally stable and where you have sort of freedom to change parameters a little bit and nothing dramatic will change. So these things are called bifurcations. These are called critical parameters. And a critical parameter is a setting of a control parameter where the phase portrait is structurally unstable, and changing it means you get one of several, in this case, two possibilities to the right and to the left, usually just two, which again are structurally stable and are different. So this is a case where the overall global behavior of a system changes dramatically if you change one control parameter. So I will give you an instruction for doing a classical experiment for a bifurcation at home. So the one of the nicest ones is if you have a water tap at home that you can fine-tune, so where you can control the amount of water that goes through it nicely. So it should be a new one that where you can fine-tune the water that goes through it. So if you open it just very little, you will get a dripping, a constant dripping, like dip, 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 and so forth. You open it a little bit more, you will get dip, 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 dip. Sounds the same, so you're still having the same system behavior, namely a regular periodic formation of drops. You open it a bit more, dip, 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 okay. Then you open it a little bit more across a critical parameter, and then you will get dip, 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 dip. You will not get dip, dip, dip. You will get dip, 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 dip. And that is, you have suddenly a behavior where instead of a single, in a sense, attractor that's just very periodic, you have a double periodic thing. So where you have dip, dip, period, dip, dip, period. And that is sudden. So you can't have any mixture of them. Do it at home. All you need is a water faucet that is fine-tunable, because you really have to find this critical point. It's very subtle. But if you have a very new and good and good faucet, you can really reliably reproduce this. And you can even continue this. So if you have a super high quality water faucet, after you have this dip, 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 and you further do it, then it gets faster. So you're still in the structural stability range, but for this double dip, 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 and then further you get dip, 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 dip. You should get 4, according to mathematical theory, and but they are structured themselves again. So these 4 should come into 2 pairs that are close together, then the longer pause, and so forth, and you would get what is known as a period doubling root into chaos. You further open it, and at some point you will have chaos. That is, there will be no apparent regularity in the dripping pattern anymore. For that you need super expensive equipment. So in your kitchen, probably not. So I think that was it for today. So I had no time for that. Phase transition. Yes, one word, just not to leave you uneducated. So, because I lived for 30 years with a terrible misunderstanding. I always thought bifurcations is the same as phase transitions, because phase transitions in physics also mean the sudden critical change of global behavior of a system if you change control parameters. However, mathematically the two have nothing in common, or almost nothing. They are very different things, and I will tell you this tomorrow morning, because I feel you all want to grab coffee instead of listening about phase transitions. Is that right? Yeah, okay. So see you again tomorrow morning.